until the quiz is over, if you can try to keep the chairs where I carefully located.
I'm allowed to ask questions.
Yes, we are now entering the period where you are free to ask questions about homework or other things that you're not quite sure of. Then we will have a quiz. And at the end of the quiz, if you're done and you hand it in, you can go take a break. Quiz. I can't imagine people needing more than half an hour for the quiz, but that's about how long we'll allocate for it. And so go ahead. You have a question?
Between C and phase shift.
Good question. Yeah, so I'm going to back up just a little here and say that a horizontal shift can apply to any function. So, for example, if I say f of x equals x squared, everybody should know that that's a parabola. And if I were to say, oh, well, what is f of x minus, I don't know, 1, take 2. Well, that's going to be x minus 2 squared. This is just a shift to the right, just like we've been talking about with the sines and cosines. And the graph would just shift over. Right? Everything just shifts over.
You take the 3 points, you move them. 0, 0, 1, 1, and negative 1, 1.
You could do that. I mean, that's how I would do it, actually, if I had graph paper and I wanted it to look nice. So this value here, the 2, that's that C we keep running into a sign of dx minus C plus D. It's just a horizontal shift. It applies to any function. Now, a phase shift, it's only appropriate to talk about a phase shift if you're talking about a periodic function. That's what we've been doing since the beginning. Functions where f of x is equal to f of x plus p for all x. As you can shift it over a period and you get the same function. So it's in that context we talk of a phase shift. And if you think about it, any shift more than a period can be restated as a shift less than the period. Right? Same way, you know, any angle that's more than 360 degrees, you can express it as less than 360 degrees. Okay. So let's go back now to something that I said that was probably confusing, which is I said, in some contexts, when you're talking about phase shift, they will use C. For example, in the example I gave for the, the triple power, where they're like, well, where there are 3 signals, they're phase shifted. Electricians would say, or EEs would say, it shifted 120 degrees, or 1/3 of the period. So you have to be aware someone might use it that way. But another way of expressing it is the shift over the period. So you could express this shift as a 1/3 and a 2/3 shift of the signals. So it's a little confusing, but it's confusing because people use it both ways. So I realize you asked a specific question. I'll give you a chance. Do you
I want to clarify something.
Yeah.
You drew 3 lines, right?
Here?
Yeah.
That's the triple.
Oh, so the first line is 1/3, the second one is 2/3?
Yeah.
Okay.
Even though the artistic rendition is imperfect.
Okay.
Okay, any other questions about phase shift means? Yes.
Actually, I have a question on that.
I'll take your question, but anybody, phase shift? Phase shift is clear?
Wait, so which one is phase shift? Would it be either?
Yes, and you would be, if it was unclear from a problem, you would be in your right mind to say, well, what are you talking about? You're talking about, you know, again, I made up this term because I thought it was appropriate, relative phase shift or linear phase shift, if you want. You know, it should be clear from the context what somebody's talking about. Or the particular, you know, if you take an EE class, you probably just know that's what we're going to use all the time. Okay, is this about phase shift?
Yeah.
Okay.
So if we have a phase shift problem, do you want us to answer in radians and degrees, or do you want us to answer in some form of units?
Well, if I ask you a question with a phase shift, either the problem would indicate pretty clearly by saying answer in, you know, radian or whatever, or you could look at the context, it might actually say, or I would have to take the answer however, right? Okay. All right. Thank you for being patient. Elliot, what's your question?
I'd kind of like to go over number 45 again.
Okay, what page is this?
On page 571. I didn't get it.
Is that the moon one or the daylight one? 42.
Yeah.
Hours of daylight. Okay. Do you have a specific question, or do you want me to go over the whole problem?
Well, yeah.
Or is there a particular A, B, and C you're interested in?
No, not really. Just that. It's not really that is. And
This is the data for hours of daylight.
yeah. I'd like to go over all of them just to be clear.
Okay. So the ACE is find an equation for the function. So we're going to use the same technique we've been using in class, which is the first thing we usually want to find is the max and the min. So someone want to glance at that and tell me the max and the min real quickly?
15.98.
Say louder.
15.98.
15.98 is the max. The min is 8.43. You know, one of the things I like about this problem is, you know, when these are kind of abstract, sometimes you can't put your hands on, you know, get your you know, hands around what's going on. But if you keep thinking about this, hours of daylight, that's something we have a real visceral feel for. It's February, January, it's kind of depressing, it's hard, right? And, you know, in the next few months we'll get more light, right? So, okay, so that's the max and the min. We want to find the amplitude, which is, actually, before we find the amplitude, let's find the midline. The midline is, how did we find this? You do what to these? You add them, and you find the average. Okay, so 24.41 over 2, 12.2. I'm just going to round. Then we also want to find the amplitude. That's minus 8.43 over 2. So what's that? 7.55 over 2 divided by 2, 37.7. I'm just going to leave it at that. Okay. What's the next thing we can find? Oh, we want to find the period, right? We want to find the period. I mean, this is D, is our D, this is our A. This is not our B, but it's going to tell us our B, right? Because the period is 2 pi, or 360 over absolute value of B. What's our period? This is one where if you look at the data, you know, yeah, it's got to be 365, right? So that means our B has got to be either 2 pi over 365, or if we're doing degrees, 360 over. All right, so we've almost got our equation. We know that it's going to look like 3.7. That's the A times. Well, let's just leave out the function we're going to use for the moment. Sine or cosine. Is there some natural kind of thing to use here? I think actually if we use degrees, we're going to get ourselves in trouble. So I'm going to use radians. And then x minus c. Oh, that's the big question. So to decide what c is, well, if we're using a sine, the sine starts at the midline, right? So any of these numbers, are any of these numbers close, any of these days close to the midline? Oh. Is midline correct? Yeah, it is. Okay, so 0. Oh! Just make it a sine. And then our C is 0. Makes life easy. Actually, again, here we go. This is a real problem. Everybody ought to know, when is that sine, when is it really? When is it really, actually, let me rephrase that. Yeah, when is it in the middle? When is it in the middle? From science and astronomy. Equinox. Yeah, it's an equinox. So that's, you know, you got the solstice, December.
The winter solstice is December 21st.
Yeah, but this is, what did they say? This is March 21st.
Well, that should be the shortest day.
Well, I think what we've got here, March 21st, that's where it's in the middle. That's the, isn't that the equinox? No. I'm sorry. Solstice is the 21st. What's June 21st? That's the,
No, that's the solstice. That's summer solstice.
Summer solstice.
Equinox is in the spring and fall.
Okay, so this is the spring equinox. Yeah, there we go. We've had a science lesson here. All right, so that's the answer to A. That's our function. Use our function to estimate the number of daylight hours when the number of daylight hours will be 13. Well, isn't what we want to do to just see, I'm not quite sure, you know, this is a question that would be much smarter for them to ask after today's lesson on inverse functions. Because really we want to find the inverse function of this function, and we want to just plug in 13 hours and then we'll pop it out. But if you look at this list here, you can see that between 0 and 30 days must cross 13, and then again, between 150 and 180 days it's going to cross 13. So I don't really want to get into, you know, you could plug in each of these numbers, 31, 0 through 31 and see which is closest to 13. The same for here. They just say estimates, so you're kind of You can do it however you want. But after today, you'll know to hit the, what happened? Oh, I hit a button. Doesn't matter. You'll know to hit this cosine inverse button. Okay, and finally, C, find the average rate of change from D equals 30 to D equals 120. William, do you need me to answer that one?
Wasn't it, it was the,
This is a Algebra 1 slope delta x delta y question. Is that clear? All we have to do is say 120, well, which is the y? Oh, that's the y. 120 over 90. And at 120, it's 15.53 minus, what it is at 90, 15.98. Except I did that wrong, didn't I? And 30. That's different. At 30, it's 14.07. And you have to multiply it by 100 because they want a percent, and then that will give you the number. Okay. Any other questions?
Can we go over, I didn't hear the answer for B.
Well, I didn't really give a good answer. I just said that they want you to estimate when the number of daylight hours will be 13. They didn't say how. And as I mentioned today in class, we're going to go over the inverse function, which will show you how to use your calculator. But for purposes of answering this question, if you just looked at this and said, well, where does the number of daylight hours change in cross 13? Clearly, between 0 and 30, it goes from 12.2 to 14.07. So if you said around 15 days after March 21st, that would be a good estimate. We'll have a better answer later today, which also should let you know that I'm not going to give you a question like that on the test quiz. Okay, any other questions? Everybody feel ready? Sure. I hope you're ready. Okay, do you need to complete something there? Otherwise, I'd like everybody to put all your stuff below your desk. You can keep a card of information, and you can keep a calculator. Somehow, magically, I have 3 calculators today.
Yep.
Only 2 of them are mine, but anyone Jonathan Bough? Okay, so we're going to be discussing something called an inverse function, guys. We're going to be talking about something called an inverse function, but we're going to take a step back and some of this you may have not run into before. I just want you to think about it a little. Background to understanding what a function is and what an inverse function is. So first I want to show you something which is what's called a relation. Relation is a little less strenuous than a function. So here we have two sets. One set, there's another set. The set has just 4 members in it, A, B, C, and D, and this has the numbers 1 through 5. And I have little arrows here pointing from the first set to the second set. This is not a function. Someone want to tell me why this is, Kyle?
Function will only have one output for each input.
Yeah, and notice the C here goes to 2, 3, and 4. Relation's a little simpler. It's just a mapping. Okay? Now, when we go to the next step, we're talking about a function. And now, you can have 2 members of the first set go to the same member of the second set. That's possible. But none of this multi-output kind of stuff. This is a very simplified diagram. We usually, when you're dealing with relations and functions, usually we don't specify individual, like every member of the set, this member goes to that member in that set, this goes to the other. Usually we have some kind of calculation we do. So, really nice. So, for example, here's my favorite demo relation. F of x equals x squared. The domain of this is, anybody? What would the domain of this function
All real numbers.
be? Yeah, it's all real numbers. And then the range would be
0 to infinity.
0 to infinity, all positive, 0, all positive numbers. So that's how we usually specify a function, at least in this class. Okay, so note that all functions are relations, right? Not all relations are functions. Okay. So now this function here, this is from set big X to big Y. This is a function, but it's also a function that has an inverse. The inverse should be really obvious. A goes to 1, B goes to 2, C goes to 4, D goes to 3. That's the function. The inverse just takes 1 to A, 2 to B, 3 to D, and 4 to C. Now, why does that work? That works because there's the same number of members of each set, and each member of the set goes to one member in the, one member of the domain goes to one member of the range. Sometimes you have a function that doesn't have an inverse. Say this one here. A goes to 1, C goes to 1, B goes to 2, D goes to 2. It doesn't have an inverse because, this backwards relation, one would have two outputs. But that doesn't mean we can't give it an inverse. The way we do that is we can remove members of the domain. If I remove C and D here, now I just have A going to 1, B going to 2, and inverse is now 1 going back to A and 2 going back to D. Now, I know that's a little abstract. I want to show you how that works with this function. F of x equals x squared. As we said, this is real numbers is the domain. The range is the real numbers greater than or equal to 0. So if we look at the kind of backwards relation, well, I can draw this here. How are we going to get this so that everything in the domain, everything in the range can go back somewhere in the domain? See, we have a problem here. Let's say we take 1. That's going to go to 1. But if we take -1, it's also going to go to 1. So we're looking at this, the inverse function here. How are we going to get something to go just from the range back here to this domain? It's not quite going to work. We're not going to be able to get to 1 and -1, are we? So in this case, we can perform this little surgery. We can say, instead of this function, which has a domain of all reals, let's take a slightly different function. This is actually a different function now, where the domain is just the positives. Essentially what we do is this. We go, now, this is a different function. It's very similar. The only difference is in the domain. But now this function can have an inverse. Does someone want to tell me what the inverse is? Should know. Square root? Square root. Now, again, I'm sure this seems a little picayune and a little obscure, but I just want everybody clear about what we're doing here. We can't have an inverse of this entire function. But, again, by doing a little surgery on the domain, now we can have an inverse. Okay, I'm going to digress just a little bit on inverses. If I have a graph of a function, is anyone familiar with how I can get the graph of its inverse? Anyone seen this before? Yeah. So you draw in this line here, which is y equals x. And then you take the mirror of it. So that's just one way graphically to get the inverse of a function. Why does that work? Well, you think about a graph as just, when you put a function on it, you're going from the x's to the y's. The inverse is now going from the y's to the x's. You're really just switching the meaning of the dependent and independent variable. So, whereas we start with kind of x here and y here, if we just, again, do a little magic surgery here, we switch the variables, that would just mirror the graph. Now, I want to show you what would have happened if we hadn't done, again, our little surgical procedure on the y equals x squared. If I took the mirror of this, what do I get? Well, I get a parabola, but why is it that we can see right away this is not a function? It doesn't pass the vertical line test. Right? You draw a vertical line here, it crosses 2 points, so it's not a function. But, again, as you can see, if I just remove this, that's the same as removing this, and now I have a function.
How do you figure what part you're moving, like way apart from left instead of part from right?
Well, excellent. I mean, first let me answer the question. How do you know? Experience. That's a bad answer. The reality is, in this case, you have a choice. Let me show you what I mean. If I take f of x equals x squared, and I take it from the reals to the reals greater than or equal to 0. So I said, well, let's just take the positive here, right? What if I just said, well, take everything that's less than or equal to 0? So now, erase this, nice and clean when we do this. Now we're saying, get rid of this. Okay? And what does the mirror of this look like? It looks like this. And what is that inverse function?
The negative square root of x.
Very good. Thank you. The negative. That's also a function. So, Judy, it was a really good question. And the answer is, there's more than one way to take a function that doesn't have an inverse and give it one. I mean, you have a choice. Usually we'll take, when we're doing this one, we'll take the positive square root, but you can take the negative square root. Okay. Look, I have all these pretty diagrams here I didn't use. Yeah, this was more fun drawing. Oh, here we go. Now, if you look at that and you get a headache, here, let me see if I can help. Oh, there we go. It's just a sine function, right? So what am I going to do with it? I'm going to draw that y equals xy, and I'm going to flip it. And now you can see I've got a problem. I want to find the inverse function of the sine, but I do a little surgery here, right? Because this is not just not a function. I mean, for every x between 1 and -1, it has an infinite number of points it goes to. So we've got to cut this down in size a little. Before I do this, I promised myself that I would take another little digression. I think I put this on the board a few minutes ago, maybe an hour ago. Does anyone know the difference between this and this? Okay, this is notation. Yes?
So is it one's the inverse of a function, the other one's the inverse of the variable put into the function? So they're reciprocal in that case.
I want one of these to be an inverse, and I want the other one to let's not use inverse.
It would be a reciprocal in that case.
Yeah, reciprocal. This is an inverse function. This is the reciprocal. This is just 1 over x. Now, to make things complicated, sometimes 1 over the function is the inverse. Like f of x equal to ax, and f inverse of x is equal to 1 over ax, which is just 1 over f of x. Right. So this is just the one exception where these are exactly the same thing. Otherwise, keep clear, these are different, and you don't want to mix them up. We probably won't see this very much. probably would be nice of me to like go like this, you know, I was going to do that. All right, some notation, keep that in mind. Okay, so back to the sign. What can we do to the sign so that it has an inverse function? Okay. Oh, it's going to tell us right here. We can truncate the domain. Okay, if we take sine of x, but we say x between pi, this is now in radians, negative pi. I want to digress one more time here. Yeah, because it'll come in handy. Have I talked about intervals? I have?
You mentioned it by saying.
Yeah. Yeah, again, we have a little notation here. Another way to write this is x is a member of this interval, negative pi, pi. Just want you to be familiar. I'm using square brackets here. And I could also use parentheses, which would mean something slightly different. Does anyone? Is there differences here? Yeah.
The curly brackets, so the square brackets on top mean that it includes the values of pi, and the parentheses means that it's up until that value, but it doesn't include pi.
That's right.
So it'll be like 1 unit less than pi.
This includes everything but the endpoints.
Yeah.
You know, in geometry, you know, you draw a little line segment like that, put a little hole here, right? This is also called, an open interval. This is called a closed interval. And you can have an interval which is kind of half and half. You could have negative pi to pi. This includes pi, but it doesn't include negative pi. And finally, you can have an interval which goes off forever. So, for example, you have something that would go to infinity, and for reasons that are, you just have to take my word for it, an interval that goes to infinity is always open. So another way of indicating all the real numbers is something that goes from negative infinity, positive infinity, again, open interval. All right, so any questions about notation? This is all good mathematical background. Any of you going on to calculus, you'll run into this a lot. Okay, so getting back here, this is negative pi to pi. All right, so what does that look like? Well, so if I can't really do what I want to do. I want to flip this. Do that with a computer. Yeah, but you can't see through it. So I just won't be able to do that. Here, I'm now looking at the inverse function. The original function, which, you know, this would be the x-axis, goes from, oh, wait a minute. Looks like I did something wrong. Yeah, looks like I did something wrong. I mean, this is the inverse sine. Anyone know what I did wrong here? I mean, if I went all the way to pi, it would kind of go like like this, and we wouldn't have a function. So the whole time I was setting this up, it's not pi to negative pi to pi, it's positive pi over 2 to negative pi over 2 to positive pi over 2. So we get rid of this, and now we have a function. If I'm ever like not showing this up on the screen, please let me know, because I don't always kind of minded that way. Okay, so let me correct myself here. We take the sine function, we truncate its domain, so now it goes negative pi over 2, pi over 2. And now we have an inverse function, sine inverse of x. So what's its domain? Domain of sine inverse of x. What values can you put in there? Yeah. You don't put it in plus. I'm going to do it this time. And what is its range? Well, there's its range. Okay. I think someone pointed out earlier that there's more than one way to do this, right? We could actually, we could change the domain and we might still have a function. So a good question is, what does this button on your calculator do? It's the second sine button. Yeah. Zoom in on this here.
We get a little closer.
Such a dramatic.
For those of you with bad eyesight,
I know I had that level of detail.
well, it comes from -1, right? To get this button,
Yeah.
Like that is. That's another
we have to press the second button here, but let's take a look here. Let's just pick some points on our graph and just make sure that we're dealing with the right inverse. All right. So first thing we want to do is check our mode. Actually, we can do it either way. Let's do it in degrees. Note that when you're doing sine, cosine, and tangent, this choice has to do with the input. But when we're doing the inverse function, this is now the output we're setting. All right? So let's set this. Let's take a point between 0 and 1, and we'll say inverse sine, 0.5. And what do we get? We get 30. 30 is what? 30 degrees, which is over here. Unfortunately, my scale is in radians, but if you think about it, convert 0.5 radians to degrees, what do you get?
It's not giving you an error. It's not a function.
What's not a function?
Inverse sine 0.5.
Well, you see, built into the calculator is an inverse, which is based on a truncated domain.
So where does it chop off the extra part?
Well, that's what I wanted to show you, is that it's the same chop that I'm doing here.
Okay.
All right. Let's say I say sine inverse negative 0.5.
Is that loaded in degrees right now?
Yeah, I'm in degrees right now. And And that's over here, negative 30, just what I was expecting.
You showed us like 100 grams plus. You showed us 100 grams plus.
Try that. So you want to see the inverse sine of x, right? Okay, apparently I need to adjust my window. Okay, so that's, I don't know if it's all on the screen here.
I would suggest doing Zoom 7, just because it looks more clear.
Okay. I have to wait and see it's busy.
Actually,
I don't know what it's doing, but it's really busy over here.
do second off, because it's going to take a long time for that to...
Second off.
Second on, sorry.
Reset that, reset.
There you go, then you just turn it on again, and then there you go.
Oh, okay. So you're saying Zoom 7?
Yes.
Yeah. Zoom 3.
Okay.
Should be there, because mine works like that. Try it again.
Yeah, I think Zoom trig is like if you have the axis the other way.
Check
It's
the
not
window.
inverse.
Check the window.
No, it is.
Yeah, see the input is negative 350, that should be the output.
Yeah. Yeah, exactly. Okay, so let me try something else.
Maybe I think it's 6.
Say Zoom. I'm gonna try Zoom square. I'll bet it'll work better if I shift it over to radians. Yeah.
Yeah, there you go. Yeah, mine's on 3. I mean, your Y max and your Y minimum are. I would suggest.
Now it doesn't even work.
Try Zoom trig again. I know it works for me. There you go.
Okay.
No.
Oh, wait.
Oh, 3.5, sorry.
There it is.
Oh, there you go. Never mind, took a while.
Okay. Technology. It was easier before we had technology.
Yeah, right.
Okay, so now we know that, at least for sine, we know what the inverse is. It's not the inverse of the big sine function, it's the inverse of this truncated sine function. Now, you're going to get a question, though, that you're going to get a question like this. Let's use the example I just used. I said sine inverse of 1/2. That was what, 30? That's what the calculator gave us. So the question you're going to get is, tell me all the possible values that will give me 1/2 from the sine function, from the, I want to say that right. Give me all the values that if I apply the sine function to, they give me 1/2. See, now we're talking about the relation. Anyone want to take a stab at this? Yes?
I think, from what I remember, the inverse sine function is like the length of the arc, and like the sine function is like how you get to the arc or something like that. But you can just derive like the length.
You may be saying something that makes sense, but it doesn't make sense. I'm not smart enough to figure it out. The length of the arc, you know, the sine function. No, we know what the sine function does, right? We know it. You know, we haven't forgotten. We haven't lost our minds here. Right? We take a unit circle. You take some angle. I guess we'll use 30. And you look at the which coordinate now for the sine? Y coordinate? 1/2. square root of 3 over 2. But now what I'm saying is I want to know every angle that when I apply the sine function to it, I get a half. See, I'm no longer just asking for the specific sine function that's in our truncated domain. So how would I figure that out?
Would it be the reference angle? Would it be the reference angle?
No, it's kind of the reference angle backwards. We've been going to the reference angle, now we want to kind of head away from it, right? So we know that the sine is, you know, wherever this goes through a half, right? So there seem to be two angles here, right? There's 30 degrees, and then what's this one? 150. All right, that's a good start. So we've got 30 and 150. Is that it? There's more. There's more where that came from. How about, I mean, you know, how about 360 plus 30, 390? Or how about negative 330? How am I going to get all those? Yeah. Except I'm going to, since I'm doing it in degrees, I'm going to add 360 n. Here I'll add 30 degrees plus 360 n. And then just, I'll let n, you know, be a member of the integers, any integer. This is the conceptual part where you start to feel steam coming out of your ears. I mean, maybe it's easy, that's good if it's easy, but because the rest of it is just, you know, the rest of this class, you know, I'm going to say this inverse and push a button, right? This is where we try and understand what the heck's going on here. Yes?
Yes, but would most of those not even matter in the inverse function? You can only use one that's restricted between pi over 2 and negative pi over 2. It would be the only 30 degrees. It's the only figures.
I'm weighing my answer here, your question. In the real world, sure, what's the difference between 30 and 390? Well, it might make a difference. Let's say you've got a, you've got like your engine turning, right, in time, and then, you know, the cylinder comes down at 30 degrees, and then at 390, and so forth. It might. So you might want to go backwards, but in the real world, generally, you're right. You don't really care. I'm asking.
I was asking something. I was saying, when we're coming and dealing with graphing and dealing with inverse functions, why do we even need to worry about anything that's outside of our domain? For example, 150 is not in the domain.
Because, okay, so if I say, you know, if we're talking about this inverse function, the one with this specific domain, the answer is clearly just 30 degrees. But there are other inverses. In other words, there are other values that when you apply the sine function to them, you get this value. And you should know how to get them all. That's all. I mean, you're right. As a practical matter, you only want one of them. As a kind of a mathematical see, this goes back to this whole relation idea. There is a mapping from this value. It's not a function, but there's a mapping to all these values. It's multiple outputs. And that's a relation, all right? Because if I said the inverse sine relation as opposed to the inverse sine function. And if I say the inverse function, if I don't mention a domain, there's kind of a standard way of making it a function. That's this, from negative pi over 2 to pi. Okay. I know someone out there is a little confused. I'm going to try and, because you're not alone. Yes.
Could you make a unit circle with inverse sine and cosine?
No, that won't work.
No?
Well, you can, okay.
Maybe
I think we can do what you want.
you just make like a triangle and show us how to.
Okay. So here's how to do it. First, let's talk about, we're talking about the inverse sine for the moment, right? So the sine is the y coordinate, right? So these are sines up and down here, right? And they go between -1 and 1. Okay? Now, give me a value that you want to find the inverse sine of. You can make one up, but just make sure it's between -1 and 1.
So let's do 0.
Okay, 0. So here's my inverse sine function grapher. Okay, so where does it cross the unit circle? Here, and here. Now, clearly that's not a function, right? So maybe I need to truncate something here. How about I do this? Okay, now we're good. Someone want to pick another function?
2.5.
Glad you did that. Oh, 2.5. Oh, that's out of the domain of the inverse.
0.5.
Oh, 0.5. Oh, 0.5. I thought you said 2.5. 0.5. Oh, that's about here. Okay.
That's 90 degrees.
Now, yeah.
And, 45.
Whatever that. Okay. We've done this one. This is actually pi over 4. But you know, you can pick something more obscure. How about like 0.7? All right. So now we can, like, at point, we find that angle. So that's how you can use the unit circle to kind of find an inverse. Right? It's just doing the inverse of what we were doing. Right? Now, if I wanted to do a, oh, this is really good. I like this. I never thought of this before. Let's try and figure out what to do about cosine inverse. Well, we know we're going to have to truncate. We're going to have to truncate the domain again to make it into a function. But what's going on with the cosine? The cosine is now the x, right? So instead of going like this, I'm going to go like this, right? So I want somebody to suggest what angles, how I should limit the domain, what angles should I limit it to, so that I have a function when I do this. So I just cross one point. I think this is really, we'll just tell you the answer in a minute, but there's a visual thing here going on. Do you see what it is, David? Yeah, you cut off the bottom part. Okay, well, what's that? Well, this is 0, and this is 180. So with the cosine, move this up a little, I want to restrict my my domain from 0 to pi. That's a little different, isn't it?
Can you also cost the top instead of the bottom?
Yes, you could. Remember, there's more than one way to make it into an inverse. Now, this is the standard way. I'm going to show you it's the standard way, the same way we did it before. I'm just going to change our function here. Let's see. Aha. Worked. I mean, if you twist this sideways, right, we're now going from 0. Did I twist it the right way? No. I'm dyslexic. Has anyone noticed visually here? We're going from 0 to pi, and the output of the inverse function is now
You can't
from...
see the calculator.
Hmm?
You can't see the calculator. It's not on the overhead. You can't see it because it's too low.
Oh, you can't see it now?
Now we can. Now we can. We're
Oh.
going to
When you were turning it sideways. you
Okay,
can't see
this is the inverse sine, inverse cosine, right?
This is too low.
At least this is when I told it to graph it.
That's all.
Yeah. Try and redraw that picture here. Remember this. It kind of looks like this is the all right. What happens if I switch that, if I mirror that? Okay. Well, this is just the cosine, right? Cosine, right? Except now we're just going from 0, the domain is just going from 0 to pi.
You only flip up one side of it? Oh, wait, never mind. That's what that one.
I'm going to redraw this. Okay, so here's my cosine. Nice cosine, right? And I'm saying what I want to do is truncate this off of it. And I want to mirror it. And I'm saying this is going to look go like this. I take this and flip it along here. I go back to my cosine, flip it now. This is my inverse cosine. All this work just to undo a cosine or undo a sine, I guess. I think it's actually a lot easier than this. It's just I'm making it as hard as possible. Okay. We have the sine. Oh, there's my cosine function. There's one more function we're going to look at that we want to know a little bit about the inverse of. That's our tangent. Okay? Remember what a tangent looks like right side up. Here it is over on its side. Inverse. Now what do we have to do? What do we have to do to the domain of the tangent to get it to work? You have to restrict the domain on the tangent function, right?
So then
we do is the same thing we did with the sine. We have our tangent function. We have our tangent function. We restrict the domain from negative pi over 2. Maybe I'm, yeah, I got it right this time. And now we have the tangent function, the tangent inverse function, which is going to go from where to where. We know it's going to go back to negative pi over 2, pi over 2. But what's its domain? What's the domain of the inverse tangent function? It's going to be all real numbers, that's right. Negative infinity, positive infinity. So you can, unlike, now let's just do a demo here. So if I said something like sine inverse 5, what's going to happen? I'm going to hit enter and I'm going to ask for the inverse sine of 5. I'm going to ask for the angle whose sine is 5. What's the calculator going to do?
It's going to freak out.
Exactly. It's going to freak out. It doesn't work. We put in a number that's not in its domain. However, the tangent, no problem. Still no problem. Right? Or if you like, minus. There's a big number in here. Still okay. All right. That's let's just do this one problem and then we'll see how far we can get. Okay, so let's take a look at this problem. Find the angle whose sine is 1 over the square root of 2. Pretty simple problem. We actually already did this. Not this particular one, but this operation. In other words, we want the inverse sine of 1 over the square root of 2. Well, sine of 45 degrees is 1 over the square root of 2. So sure, that's right. Is there any other angle that could be true of?
The reference angle of 45? 135 degrees.
35 degrees, right? Again, we're taking, for the sine, we're taking a horizontal line, which is 45. Now here we have 135. All right, so we have 45 and 135. What else? What other angles have a sine of 1 over the square root of 2?
The reference angle, like the opposing, or is that negative?
This is the reference angle.
All of those plus this.
I mean, the opposite of that, the space between 45 and 180.
180. The 135. That's over here. No. But let's look into that. Right? Here's 225, right? Why is 225 not an angle whose sine is 45? Well, what's the sine of 225? It's negative 1 over the square root of 2.
So does that mean
not one of the answers to our question. Right? So there are other angles, right? And we know all of them. It's just plus 360n plus 360n, again, where n is any integer. That's all of them. It's an infinite number, but that's all of them. Here they are. Here they are. Okay. I have a handout. We don't have really much time here, do we? Maybe we can do the first problem. No, actually, the first one's really easy, so you can do the first two problems. This came in everybody pretty fast, so we'll talk about this on Tuesday. We'll talk about inverse sine inverse functions. And before we completely fall apart, hello, there is an assignment. There is an assignment for a homework assignment for this section, although it won't be due till Thursday. Is that right? Yeah. So for February 3rd, section 8.6, a few problems listed here, page 585. Okay, so you might want to get started with those. Wait a minute. Today is Thursday, right?
Yes. How much I give. It's like a high school, I don't want to be.
It's funny, I thought I always kind of gave people the weekend. Well, I would be giving. I guess this is due on Tuesday. Okay. Give it a shot. We'll go over it in class.
I'm sorry, which number?
Number 7.
Number 7 ending or just 7?
Number 7.
Okay.
Wait.
They have the same beauty.
I have to admit, I'm just looking at numbers here. I'm really confused. Let me look this up before I. Oh no, I see. 8.6. That was the other. Okay, we did 8.6. 8.6 and 8.7 are both due on Tuesday. Please, for number 8, 8.7, all that stuff, read my note. My note says, when asked, you do not have to explain. It's going to say, explain this, explain that. Do not explain. Do not explain. Not.
You've got the other, parentheses, right?
Right. Well, this is not a computer program.
What's the range?
No, I'm just kind of making a note and opening up a note. I'm not closing it though. The world will not end, I assure you.
Number 7 says even 40 and 41, we're having.
Sir?
Number 7.
8.7?
8.6.
Oh, 8.6, yeah. That's a homework from what we did 2 days ago.
Oh, we already did that?
We already did that section.
Oh, okay, but what does even 40 and 41 mean?
It means number 2 to 26 even,
Oh, okay.
and then 40 and 41.
Got it.
All right. Somebody, someone have the, I can erase this. Someone have the answer to that first problem yet? Sine equals 0. The angle whose sine is 0. 0 degrees, 180 degrees. But it says find all the possible values.
So do you want us to go like y and then actually in this case we could just do 0 plus 180 and
Yeah, I know.
from up to up.
For sine?
Is that maybe on like 540 for the first one also?
And the rest are close to
Would you want 540 for the first one also?
Okay.
I want all of them.
That's like more than I have space on paper.
That's correct. That's more than all the paper in the universe.
Yeah, I should remember.
But if you write it like this,
Yeah, should that one.
and if you somehow indicate to me that n is, integer,
But then, okay, so then
let's plan the first thing on Tuesday. Take a look at the last, do the other two problems, they should be easy, but take a look at the last item, find the domain. We'll talk about that on Tuesday.